So today we are going to start with diffraction grating. You already know about the concept of diffraction, right? We studied about reflection, refraction, and diffraction, and this concept is actually a concept. And grating is basically a type of element. We can say that it's simply a piece of glass, or we can say that piece of a plastic. And the purpose of this grating element is, let's suppose if we take a small piece of plastic or glass and we just make scratches on it maximum as you can in uniform pattern, right? So actually this material is known as element. Basically, a grating element is made up of plastic or glass which contains like 300 lines per millimeter, 200 lines per centimeter, like this. So as much as we can draw a lines on that piece of paper, plastic or glass, so that will act like a diffraction grating element, right? Because we know in diffraction, we need to deflect light through the edges. So that's why we mark as maximum lines in very short length, right? So this is the concept of diffraction grating. Okay. And now we need to form an equation to find out the unknown values like the wavelength, like the angle, and we also need to talk about the orders of bright fringes and dark fringes, right? So
Yeah,
first of all, the basic, if let's suppose if they ask what is diffraction grating, or so you may just simply write that diffraction grating is a plate on which there is a very large number of parallel identical closed. So this is the explanation for this diffraction grating. If someone asks in exam that what is diffraction grating, so you simply write this definition, and mostly it is made up of glass or plastic because that is transparent and that will easily change the medium of the light to, and that was completely transparent. So that's why we use plastic or glass for diffraction grating element. And also we know that we are using monochromatic light because we need a single frequency, single wavelength. So we also going to use a single wavelength or monochromatic light in this experiment. And let's suppose if a monochromatic light is moving from one end to the diffraction grating, so on screen we are going to have pattern like this. Let's suppose if we are moving from left hand side and grating element is placed over here. Now light starts to split in different angles because of diffraction. So this is a simple concept of diffraction, and we are getting fringes on screen. So these are the fringes we are getting on the screen, and you know that when we are getting a light on the screen, so that gives you the concept of bright fringes, and when there is no light on the screen, so that part shows you dark fringes. So in this diagram, actually this part shows you dark fringes because there is, and these green lines shows you bright fringes. Okay, now if we want to find the unknown quantities, let's suppose if we want to find out the angle, if we want to find out the order and the wavelength, so the formula for diffraction grating is d sine theta is equals to n lambda. This is the formula for diffraction grating. Theta is for the line used for the order, just like in young double slit experiment, order number 1, 2, or 3, and lambda represents you the wavelength of the light. So actually we are using monochromatic light over here.
Wait, what does the D stand for?
Yes. So actually D is a new quantity that we are going to discuss in diffraction grating, because the concept of diffraction is related to number of lines. So actually D gives you the concept that how many lines we are going to mark in single centimeter, millimeter. So it depends upon unit, or maybe in nanometer. So actually this D represents you spacing between adjacent slits. And in most of the question, times they ask you to find D, because they just mention, let's suppose they mention in the questions there are 600 lines per centimeter. So let's suppose if you want to convert into meters, so it's up to you that how you are going to convert. Sometimes they ask in nanometer, sometimes they ask in millimeter. So you just need to use this formula. D is equals to 1 over capital N. So it means that in 1 millimeter, let's suppose now on right hand side with 1, we need to write the unit. Unit may be millimeter or centimeter or meter. Okay. So with 1, we are going to write the unit that is given in the question divided by total number of lines. Okay. So that will give you the value of small d. Let's suppose if we are calculating 1 millimeter. So in question, it mentions that there are 300 lines per millimeter. So this is value of D. And now if you want to substitute in the equation, so you will substitute like 1 millimeter divided by 300. Okay. So that will give you the value of D. So let's suppose if you want to convert into meter, so you may just simply convert into 1 into the power minus 3 for milli divided by, and after dividing the value, you will get the answer in meter, right? So this is the concept of small d.
Okay.
And n remains same. That will give you the order of maxima, because we usually work on the bright fringes, because dark fringes are like unknown black marks. So actually we consider bright fringes. So this is the distance from the center to the first order, second order, third order, and wavelength sine theta gives you the same concept. You already know about the theta and wavelength. So let's suppose now if we want to talk about the angles, that how we are going to find out the angles, and what will be the change in angles if we increase, decrease intensity, or like this. So let's suppose one more point over here, angular separation Angular separation means angle between two bright fringes or angle of any bright fringe from the center. So that means angular separation of each maxima is calculated by rearranging the grating equation to make theta the subject. Is also very simple concept. If we want to find out the theta, so we need to arrange equation like this, that theta will be our subject and all quantity will be on the other side. So this is also a simple concept. And the remaining part is very simple. Let's suppose if we consider this one as the central maxima n equals to 0. So this is our central maxima. This is our first order on right hand side. This is our first order on left, and this is our second order on left hand side. So orders are going to be like this. And if you want to find out the angle, so let's suppose if you want to find the angle for the first order, so for the first order your angle will be like this. You need to measure from the center. This is your theta number 1 because this first order. And same if you want to find for the second one. So for the second one, you are going to make the same angle from the central maxima like this. So that will give you the value of theta 2. Okay, so same goes for third, fourth, and fifth order. And let's suppose now if you want to find the angular separation between theta 1 and theta 2, so you just need to subtract theta 2 by theta 1. Okay, so that will give you the angular separation. That is also simple. Okay, one more thing. Let's suppose someone asks you that if we want to find out the order of maxima, or so at which angle you are going to get maximum angle to see maximum order or maximum value of diffraction grating. So at which angle it is possible, the highest order of maxima. If we want to find the highest order of maxima, so at which angle we are going to have the maximum order or the highest value of the maxima. We know that we are using sine theta in our equation. So sine theta will be maximum at 90 degree. So it means that at 90 degree, we are going to have the highest order of maxima. So your theta will be equal to 90 because sine 90 is equals to 1. So at 90 degree, we will get highest order of maxima. And your final equation will be d is equals to n lambda. Okay. And one more thing, let's suppose if we talk about that small n, since small n must be an integer, so let's suppose if the value, then it must be rounded down. And let's suppose, for example, we are having value. We calculated n, which is 2 points. So we need to round off like this. N is equals to the highest order visible. So let's suppose if we are getting answers in decimal, so we need to select the least value. Let's suppose 2.7. So we can easily round off to 3, but we select 2 because that was the highest order visible as close to the central maxima, right? Because angle 3 or the third order is now at greater angle from the central maxima. So that's why we choose highest order visible, right? Because as far as you move away from your center, so your intensity of light is going to be decreased as compared to the intensity of light at the center, right?
Okay.
And the last thing in this chapter and this topic is, let's suppose if you want to find out the wavelength or lambda from the diagram. So let's suppose if we consider diagram one more time. So this is our diffraction grating and this is the screen. And we are using laser light because laser light is monochromatic. It strikes the grating element and it simply moves in a straight line from the center. This is our center line. And after that, it will diffract in different angles. Like this will be our angle 1. This will be our angle 2. Same goes on the other side. So now we are having different angles, and on these different angles, let's suppose if we start from the center, this is our theta number 1, because this is the maximum order, this is the first order, and this is the second order. And same goes on the upper first, second. And for theta number 2, we will take this. This will be theta 2. So now what we need to do, we need to find out the wavelength from the diagram. So how we are going to find out the wavelength from the diagram? Let's suppose from the diagram from the center, we consider the second order from the central line. So starting from the central line, if we consider this total distance, so this will be our vertical height from the center. And in last topic, we discussed that the distance from the slit to the screen is equals to capital D. So again, if we use that concept, so the distance from this the screen will give the value of D. So this is the value of D. And now if we use the quantity of tan theta, so tan theta is equals to perpendicular upon base. Tan theta is equals to perpendicular upon base. And on perpendicular, we are having our height. This is perpendicular. And this is our base. because we are getting like right angle triangle. If we just draw a 90-degree over here, so we are getting a pattern of first order and second order in right angle triangle. So that's why we are using the base and perpendicular, because both quantities gives you the concept of tan theta. Perpendicular is equals to the height, base is equals to capital D. So that is the concept of uh, the wavelength or the theta if you want to find out from the diagram. So your final lambda will be equal to d sine theta over n, because actually we are using a base with d, and d means that it depends upon the number of order from the center, and d sine theta gives you the concept of same the angle and the grating element, the number of lines per millimeter or per centimeter. Okay. And from
Okay.
yes, and from this equation, if we are using this equation from the diagram, let's suppose if they want you to calculate the angle from the diagram only, and the values of wavelength, small d is not given in the question. So you may also find from the diagram, because you know that theta will be equal to tan inverse h over d, right? Because tan theta is equals to h over d, and if we just want to find out the angle, so theta will be equal to tan inverse h over d. Okay,
Okay.
so this is the experiment, right?
Got it.
Okay, any confusion, any question from other topic in this chapter?
No.
And this is the last topic of your waves and superposition section. So that is the end of your wave section and superposition. But still we need to solve many questions, because that will give you the concept how the concepts are going to be applied in our final exams. So that is very much important. And after the class, I will also share a video that is the practical explanation of that diffraction grating, that how we use this experiment in our practical labs to find out the value of the wavelength. Because in practical, we use sodium light. Sodium light is also, we can say that, a monochromatic light. So we are not using laser in laboratories, we use sodium light, and by the help of that experiment, we find out the actual wavelength of sodium. So I will also show you that. Okay.
Okay.